Imagine this. We wrap a rope once around the Earth's equator, pulled perfectly snug against the ground, without a single gap. Its length, about 40,000 kilometers. Convert that to meters and you get a staggering 40 million meters. And this is where today's story begins. A hair-thin intuition, and its betrayal. We cut the rope and splice in exactly 1 meter. That's 1 part in 40 million. A drop in the bucket. We lay the lengthened rope back around, hovering at exactly the same height everywhere, just barely off the ground. How high does it float? Most people answer like this. It's just 1 meter out of 40 million, surely thinner than a single hair. Sounds so plausible, and it is so wrong. The correct answer? About 15.9 centimeters. That's a gap a cat can stroll through. The gap made by a single meter is wider than your palm. The rope around the Earth puzzle has been fooling people for centuries, but the surprises don't end there. First, this 15.9 centimeters is exactly the same whether it's the Earth, a basketball, or the sun. Second, take that same 1 meter, grab the rope at a single point and pull, and the gap soars to the height of a 40-story building. We'll unravel both tricks in turn, then set them side by side at the end. Our only tool, the circle circumference formula from grade school. Now it's time to unmask the magic. The formula for the circumference of a circle, do you remember it? The circumference C of a circle with radius r is 2 pi r. This one formula is the beginning and the end of today's story. What matters here is that circumference and radius are always locked together in a fixed ratio of 2 pi. When the circumference grows, the radius grows in proportion, and the exchange rate is always the same, 2 pi. We add delta L 1 meter to the rope. For the new radius r prime, the formula still holds. Inside the original circle, outside the new rope circle. Now let's stack the two equations and subtract. On the left, C cancels and only delta L remains. On the right, all that's left is 2 pi times the difference in radii. Call the gap height we wanted h, and the answer is astonishingly clean. Delta L over 2 pi. The gap is the added length divided by 2 pi. That's all, nothing else is needed. Let's plug 1 meter in for delta L. 1 over 2 pi, out comes roughly 15.9 centimeters. Now let's flip the question. To lift the rope 1 meter off the ground all the way around the Earth, how much would we need to add? Flip the equation around and delta L is 2 pi times h. Set h to 1 meter and you get 2 pi meters. About 6.28 meters. Splice in just that much and the rope rises exactly 1 meter around the entire Earth. It's rare to feel pi become this tangible, and yet the real shock hasn't even begun. Now we reach the heart of this journey, the most shocking truth of all. Let's take another look at the formula we just derived. The answer is delta L over 2 pi. But look closely at this formula. Doesn't something seem odd? Nowhere on the right side do you see the original radius r. It has vanished without a trace. Whether the circumference is 40,000 kilometers or 4 centimeters, it has no place in the answer at all. Wrap a rope around a basketball and add 1 meter. It lifts by 15.9 centimeters. The Earth, the same 15.9 centimeters. Even the Sun, exactly the same. It is independent of size. Let's verify it with code. Add 1 meter each to a basketball and to the Earth and the output is just a single line. Why does this happen? Because circumference and radius are inseparable partners. They always move hand in hand. When the circumference grows by 1 step, the radius follows by a fixed stride. That stride is 1 over 2 pi. The fact that the original circumference was enormous tells you nothing about how much it grew. In the language of formulas, it's even simpler. Delta C equals 2 pi times delta R. The big R itself has already cancelled out of both sides. All that remains is the relationship between the changes. Add 1 meter anywhere and it creates the same gap. That relationship leaves no room for the original size. Now let's nail down the size independence from the last section with a single graph. The added length delta L goes on the horizontal axis, and the resulting gap h on the vertical axis. The formula is delta L over 2 pi. A straight line through the origin with slope 0.159, direct proportion. There is no radius r in this line. Basketball, Earth and Sun all trace the very same line. We said the lines overlap, but do they really? Let's draw them for 3 different sizes and see for ourselves. Can you see the 3 lines? Actually, you can't because they overlap perfectly into a single line. That's why we deliberately drew them with different thicknesses and line styles, just enough to tell they share the same spot. All 3 lie on one straight line. It's the most honest proof that the radius has no place in the answer. Add 1 meter, and the gap is about 15.9 centimeters. Add 2 pi meters and it's exactly 1 meter. Let's sum up. The gap is always delta L over 2 pi, completely independent of the size of the ball. And that was Act 1. Now let's flip the whole stage upside down. So far we've shared that 1 meter out fairly 16 centimeters of lift everywhere. Now shall we get greedy? Keep the rest of the rope pulled taut against the ground, grab just one point, and hoist it straight up into the sky. The rope is no longer a circle. From either side of the apex, 2 straight lines stretch down and just graze the ground. Why straight lines? A taut rope takes the shortest path, and the point where it just leaves the surface is the point of tangency. Here's a common misconception. Only the 2 tangent segments lift into the air, the long arc stays flat on the ground. Now for the geometry. At the Earth center, we'll call the angle between the vertical axis and the radius to the tangent point alpha. Each lifted tangent segment is our tangent alpha, and the long arc on the ground is our times 2 pi minus 2 alpha. Add these together, and the total must equal the lengthened circumference. 2 pi r plus delta L. Simplify and you get a clean transcendental equation. Tangent alpha minus alpha equals delta L over 2r. From the right triangle, D is our over cosine alpha, and the height is our times secant alpha minus 1. Plug in a radius of 6,378 kilometers and 1 meter, solve, and alpha comes out to about 0.00617 radians. Look at what the computer spits out. The height of the 1-point pull is a staggering 121.5 meters. A height to rival a 40-story skyscraper, rising from a single point on the rope. The angle in the diagram is wildly exaggerated so you can see it. The real alpha is a mere 0.35 degrees. Compare that with the 15.9 centimeters of the uniform lift. A staggering 763-fold difference. The orange curve, the 1-point pull, leaves the green line of the uniform lift far, far below. The same 1 meter, 2 very different fates. Why do they differ this much? It's time to dig into the reason. At last, we've arrived at the heart of this paradox. The answer hides in the difference between division and a cube root. It's the same 1 meter. So why is one side 16 centimeters, and the other 121 meters? Act 1 was independent of size, so does this one depend on the Earth's size? The answer lies in how the slack gets spent. Lift it evenly, and the 1 meter spreads around the whole circumference divided by 2 pi. It's plain division. Pull at just 1 point though, and the slack is spent only on the tiny difference between the arc and the tangent lines. And that difference is stingy. Tangent alpha minus alpha is, for small angles, almost alpha cubed over 3. The curve hugs the floor. To free up the same slack, the angle has to open much wider, and the huge radius amplifies that angle into height. Write it as proportions and the fates split. Uniform lift is delta L over 2 pi independent of size. The 1-point pull goes as the cube root of r times delta L to the 2/3 power. Depends on size. If the Earth were bigger, it would rise even higher. Act 1's magic vanishes cleanly here. One caveat. This cube root only holds when the slack is far smaller than the radius. A basketball breaks that condition. Let's check. The approximation's 121.5 meters matches the exact value down to the decimals. In the uniform column, all 3 read 15.92 centimeters, but the 1-point column grows and grows with size. A basketball gives 0.558 meters, the Earth 121 meters, and the Sun soars to 580 meters. In the end, how you distribute the slack is the switch that turns size dependence on and off. The contrast is carved right into the formulas. Maybe words and pictures aren't quite enough. Now it's time to get your hands on it. The widget has 2 sliders. The top one sets the ball's size, the bottom one the length of rope you add. There's no trickery. Tangent alpha minus alpha equals delta L over 2R, solved live by bisection. First, uniform mode. Sweep the ball from a basketball all the way to the sun, the number doesn't budge. The gap is delta L over 2 pi. Basketball, earth or sun. It's 15.9 centimeters every time. Now toggle to the 1-point pull. The same 1 meter, and the landscape changes completely. As the size grows, the apex shoots up alarmingly, from 0.558 meters all the way to 581 meters. You can feel the difference between the 2 kinds of magic right at your fingertips, not as numbers but as a sensation. This puzzle is actually quite an old guest. Now let's turn to its history, and to a railroad track in the height of summer. By tradition, it is said to have first appeared in a 1702 work by the English theologian and mathematician William Whiston. That said, sources disagree on the exact first appearance. The safe claim is simply that it was circulating around that time. This was the man who succeeded Newton in the Lucasian chair at Cambridge, tackling a puzzle that looked like a joke. But this is more than a parlor trick on paper. Picture a railroad track on a sweltering summer day. Metal expands in the heat. Even a slight lengthening of the rail makes the excess burst upward, and that's buckling. A rail pinned at both ends has no way to spread the extra length evenly. It piles up in one spot just like the 1-point pull. That's why railroad engineers deliberately leave gaps between the rails. Those are expansion joints. It isn't literally the same equation as our tent formula, of course, but the intuition is identical. A tiny elongation amplified into a huge rise. The grand finale. Let's return to the original question and gather up what just 1 meter has taught us. Add just 1 meter to the circumference of the Earth. How high does the rope lift? Now we know the answer. The same 1 meter. Yet depending on how you handle it, 2 completely different worlds opened up. Lift it uniformly and you get delta L over 2 pi, 15.9 centimeters. There's no size in the formula, so even the sun gives the same answer. Pull it all up at a single point and you get roughly 121 meters, a 40-story building. This time it grows with the cube root of r. We were so captivated by that ratio 1 in 40 million that we missed the point. It's the change itself that decides the answer. Overwhelmed by the enormous number, we failed to see that this very number cancels out and disappears. Mathematics' gift is picking out what truly matters. Erase the 40 million meters, and all that remains is a 1-line formula and 2 pi. Next time that certainty arrives, of course it must be so. Try unfolding it to see what's tucked inside. If you enjoyed today's video, please subscribe, like, and turn on notifications. See you in the next story.